Lesson 13 is key features from rules of cubic functions, and then 13.1 and 13.2 kind of break down those key features into two different sections. 13.1, we're going to focus on domain, range, y, and x-intercepts. So in example 1, find the following key features of f of x equals x minus 4 times x plus 2 times x plus 5. So this is what's in called factored form, and cubic functions in general are something that has like x to the third power. So in its like most basic form, it would be f of x equals x to the third. There could be like some x squareds in there and x to the first power and so on, but x to the third power, that's like the highest power over x. And then with example 1, this is in factored form. You can always tell I guess if a function is like a cubic function or what type of function it is by counting how many x's are being multiplied together. So this has 1, 2, 3 x's being multiplied together. So if I were to like FOIL and multiply this whole function and get it in standard form, it would end up with x to the third power. So it is a cubic. And then for a cubic function, domain and range is always all real numbers because, you know, I can cube any number that I want. Like I can take any number and raise it to the third power. And then also when I cube a number, I can get a positive or a negative depending on what the base is. So like for quadratics, the range is not all real numbers because if I, let's say I put in a -2 and I square it, that would give me a positive number. So I can only get positives out from like x squared or quadratic in general versus a like cubic function. If I take the same -2 as my input value, raise it to the third power, and -2 to the third is -8. So I can get negatives out this time, which is why the range is also all real numbers. So just a couple different ways to write domain and range and just all real numbers in general. So for domain, just written out in words, all real numbers. I did not leave myself enough space to write it out. And then same thing for range. Range is all real numbers. And then a symbol that we use a lot of times to represent all real numbers is an R with an extra line through it. So capital R with an extra line. And then another way of writing it is with inequalities. We've talked about those before. We haven't used them that much. But for domain, domain is all the x values. So to write all the possible numbers, you would say x is less than infinity and greater than negative infinity. And then for range, it's kind of the same idea. I'm going to say, in this case, I'm going to say y instead of x since range is all of our output values. You could also do like f of x, depending, I'll change it to f of x actually, but basically range is like all of our output values. So it'd be f of x or y is less than infinity, greater than negative infinity, just all possible numbers. And then there's also interval notation, which is the one that's like between parentheses or brackets. So all real numbers would be negative infinity to positive infinity and parentheses around it. Brackets for when you can like include that number, and we can't include infinity because it's not an actual number. Range is the same, so all real numbers negative infinity to positive infinity. We're not going to write out like all three different ways every single time. We'll just use interval notation for like the future examples. Okay, so for the next key feature is y-intercept. So to find a y-intercept, you have to substitute in x equals 0. So it just means wherever there's an x in the function, we put in 0 and we solve. And whatever number we end up with is going to be our y-intercept. When the same thing applies here, like where if this was in standard form, that a constant would give us the y-intercept. We'll see that with example 2. So for y-intercept, we'll find f of 0. So we take a 0, put it in for all the x's. So this right here would become 0 minus 4 in the first parentheses, 0 plus 2 in the second, 0 plus 5 in the third. Oops, 0 plus 5. And then we'll simplify and multiply everything together. So 0 minus 4 is -4, 0 plus 2 is 2, 0 plus 5, 5. And then if we multiply the 3 together, -4 times 2 is -8 times 5 is -40. So we end up with negative 40 from our f of 0, which means that our y-intercept is negative 40. And then for the x-intercepts, that's when we find the zeros of the function. So when we want to find the zeros of the function, we replace all of f of x with 0. So like this 0 would just replace the entire thing. It wouldn't become like f of 0. It just becomes 0 equals, and then the rest of the equation or function would stay exactly the same. So x minus 4, x plus 2, and x plus 5. So this is already in factored form, so the kind of the harder work is already done for us. Now we can just set each factor equal to 0. So one factor is x minus 4, set that equal to 0. And then x plus 2, set that equal to 0. And then the last one, x plus 5, set that equal to 0, and then use inverse operations to get x by itself. So add 4, 1 x-intercept is going to be at 4, and then subtract 2, 1 will be at x equals negative 2, and then subtract 5, 1 will be at x equals negative 5. I personally don't have a preference on whether you write your like x-intercepts as x equals 4, negative 2, and negative 5, or write them as a point, but just for the sake of practicing, remember that x-intercepts have a y-coordinate of 0, so at x equals 4, that would be the x-intercept of 4, 0. This would be negative 2, 0, and then negative 5, 0 for all of our x-intercepts. And then I'm going to go back and write our y-intercept that way. So if we have a y-intercept at negative 40, a y-intercept has an x-coordinate of 0, it'd be 0, 40. Okay, and then moving down to example 2, find the following key features of f of x equals negative x cubed plus 3x squared plus x minus 3. So same stuff, domain and range, like for any cubic function, which this is a cubic function because the highest power over x is a 3, unless it's like a word problem where it's providing you with context, the domain and range will always be all real numbers. So I'm just going to write it in interval notation, which is the one with parentheses. So domain, it's all possible numbers, so or all real numbers, so negative infinity to positive infinity. Same thing with range, negative infinity to positive infinity. And then for the y-intercept, the same kind of like shortcut they use for quadratics works here also, where if it's in standard form, which our function is in standard form, the like constant value in this, like for cubics, they call it d, but whatever the constant value, that's the number without the variable, is your y-intercept. So our y-intercept is going to be negative 3. If you don't remember that, it's really not a big deal. You could find the y-intercept the same way as we did with example 1. So we would do f of 0. So we plug in 0 for all of the x's. So right here, 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 and then see what we end up with. So it'd be negative 0 cubed instead of x cubed plus 3 times 0 squared plus 0 minus 3. 0 cubed is 0, so it's nothing. Order of operations, if I square 0, that's 0, and then times 3 is still 0, so nothing, plus 0, and we just end up with that constant term, negative 3. So either way, whatever way works, basically like main thing to remember is if you don't remember that the constant is the y-intercept, put in 0 for x and you'll find it. Okay, and then just to write it as a point, 0, negative 3 is our y-intercept. And then for x-intercepts, same like initial approach, we're finding the zeros. So that means that we take 0, put it in for all of f of x, so the whole thing would get replaced with it as opposed to just x. So we put 0, and then it would be equals negative x cubed plus 3x squared plus x minus 3. And then we're trying to solve this now. So since this is not a quadratic, it's a cubic, we can't really like use quadratic formula or anything like that. Doesn't apply here. We would just basically want to try to factor it. It would be the main way to solve it. And this has 1, 2, 3, 4 terms. So if it has 4 terms, we're going to try to use factor by grouping, which is when you split the well, assuming it's in standard form, you split the one side of the equation in half and kind of group them together by pairs and then factor out the GCF from each half. So we'll bring down to 0. And then from the first half, so negative x cubed plus 3x squared, the GCF of the coefficients will just be 1 since the lead coefficient is -1, and then they both have at least x squared. Whenever the first term is negative, though, like I like to factor out a negative, usually just helps the problem work out a little bit better. So for my GCF, I'm going to do a negative and then x squared. Remember, for the variables, you can pull out the lowest amount that they both have in common. So they both have at least x squared, so I can pull that out. And then when I factor out GCF, that's like undistributing something from the pair. So I'm dividing it out. So if I do negative x cubed divided by negative x squared, and negative divided by a negative would turn it into a positive, and there'd be just x the first power left. And then 3x squared divided by negative x squared would become negative 3. And you can always check your, I guess, factoring by distributing back. So like negative x squared times x would bring me back to negative x cubed. Negative x squared times negative 3 would bring me back to a positive 3x squared. So it works out. And then we repeat the same process with the second part of that side of the equation and that side of the equal sign, so x minus 3. There's like no GCF other than 1. There's always at least a GCF of 1. So even if the GCF is just 1, we do factor that out. So we write it as plus 1. And then if I'm factoring out 1, nothing changes. It's dividing it by 1, so it doesn't change the value. So I'd be left with x minus 3. And then in this next part, it's really important that what's left inside the parentheses is exactly the same. So x minus 3 and x minus 3. Had I not factored out a negative here, I would have had to go back and fix something or factor out a negative out of the second half if I wanted to. That probably would have looked funky. But just keep in mind, like, what's inside the parentheses needs to be exactly the same, including the signs. And then now what I've done is I've created 2 terms. There's one right here, and then this is a second term over here. Each of those terms has a common factor of x minus 3. I'm going to pull that out of both. So it'll be 0 equals, I'm going to pull the x minus 3 out inside parentheses, and then what's left over becomes its own binomial factor. So negative x squared plus 1. I'm going to put the positive 1 in front just for no reason other than it being positive. So it'll be 1 minus x squared. And then honestly, if we had pulled say we had done a positive here, and then I would have had to do a negative here to keep the signs the same, it works out the same way. So you don't have to do it one way or the other specifically. As long as you're following the correct practices, you'll end up at the same final result. Just kind of depends on how you're viewing the problem personally. Okay. And then now we want to make sure it's factored all the way. This is a difference of squares because 1 is 1 squared. So remember, the difference of squares pattern is a squared minus b squared. That factors into a plus b times a minus b. And then so my a would be 1, my b would be x. It doesn't always have to be the variable in front, it just is a lot of the time. So it'll be 0, and then equals, I'm going to bring down the x minus 3. And then this is going to factor into a plus b, so it'd be 1 plus x times a minus b, so 1 minus x. And then now it's completely factored, so I'm ready to set each factor equal to 0. So one factor is x minus 3, set that equal to 0. One factor is one factor is 1 plus x equals 0. And then one factor is 1 minus x. Set that equal to 0 as well. And then solve each individually to get x by itself. So for the x minus 3, I would have to add 3 to both sides. That would give me an x equals 3. Sorry about the little kind of squished writing. And then for the second equation, I would have to subtract the 1 over. That would give me an x equals -1. And then for the third equation, I'm just going to add the x over so it'll become positive. And then that leaves me with x equals +1. So I have for my zeros, x equals 3, x equals -1, and x equals +1. Just to write them as actual points for the x-intercepts, that would be 3, 0, -1, 0, and 1, 0. Okay, so we're good with example 2. We found everything that we need. We're going to go on to example 3. Fortunately, later on, we take a lot of these kind of same repeat problems and analyze them further, so we don't have to do this work again with a new version of the problem. So example 3, find the following key features of f of x equals -x plus 2 cubed. I talked about in example 1 how you could tell it's cubed because you see 1, 2, 3 x's being multiplied together. Here we only have the 1, but it's being raised to the third power. So if I were to expand this, it would be x plus 2 times x plus 2 times x plus 2 3 times, and it would look almost like example 1, just different numbers. Okay, so example 3, domain and range, nothing changes here, it's all real numbers still. So for domain, goes from -infinity to +infinity. For range, same thing, all real numbers, -infinity to +infinity. For the y-intercept here, there's no real shortcut to find it. We have to put in x equals 0 and solve. So we'll put x equals 0 in here, and then we'll simplify. So we're finding f of 0. So it'd be negative, don't forget the x, it's not hidden, but it could be easily skipped. And then parentheses, 0 is going to go in for the x right here. So it'd be 0 plus 2 to the third power. And then negative stays out in front, add inside the parentheses 2 to the third power. And then the negatives out in front of the parentheses, it wouldn't really make a difference if we viewed the negative with the 2, but it's just better practice to not, in case it ever did make a difference. It could with even powers. So we take the 2, we raise it to the third power, and then we just bring the negative down. We're not raising the negative to the third, even though the outcome would be the same. It would be different if we had an even exponent, but 2 to the third is 8. So we end up with f of 0 equals -8 once we bring the negative down, and then that's our y-intercept, so we'd write it as 0, -8. And then for the x-intercepts, same concept, so it's the same concept all the way through. We're finding the zeros. That means that we take a 0 and we completely replace f of x with it, so it would become 0 equals negative parentheses x plus 2 to the third power. And then now we just want to go ahead and solve for x. So this is technically already in factored form as well. There's a couple of different ways that we could view this. If you wanted to, you could, air quotes, cancel out the negative by dividing by a negative, but 0 divided by negative is still 0. We could also technically cube root something here, but because this is 0, we're just always going to end up with 0 on the left side of the equation. So really all we need to do is just focus on this one factor, because even though it is the third power, it's the same factor over and over and over again. It's going to give us the same 0 over and over. So we'll just do x plus 2 equals 0, and then subtract over the 2, end up with x equals -2. So x-intercept at -2, which would show up on the graph at -2, 0. So this technically, even though it was a higher power, it just shows up as one x-intercept. It changes what's called the multiplicity of the root, which is something we're going to talk about later on in this lesson. Okay, so more key features. This is end behavior now. So we've talked about this a little bit before already by looking at a graph. End behavior for a cubic function, it always goes in different directions. So if this is standard form, f of x equals ax cubed plus bx squared plus cx plus d of a cubic, just like a quadratic, the lead coefficient, a, tells you what the end behavior is going to be because it tells you if the function is increasing or decreasing overall. So the graph on the left is like, think like kind of like positive slope, even though that's not what it is because it's like curving, but it is like trending up and to the right, which is like what a positive slope would do. So we're going to have a positive lead coefficient. So for this one, we'd say a is positive. And even though like the graph may look different depending on what the function is, it'll finish the same. So anytime a is positive, it's going to go up and to the right and down and to the left. So for end behavior, as x approaches negative infinity, that's the left side of the graph, f of x approaches. So on the left side of the graph, it goes downward. So f of x approaches negative infinity. And then for the next line, as x approaches infinity, that's the right side of the graph. The right side of my graph finishes upward. So f of x approaches positive infinity. And when you're writing end behavior for a cubic, these should always go in a different direction because a cubic function, it's like their tails will always go in different directions. And then the graph on the right is trending down and to the right. So if I were to kind of like draw like a line through the graph, you can see that line has a negative slope. That means that the lead coefficient would be negative. So a is negative. So even if the specific graph looks different than this, like the function's more complex and stuff, or it's in a different area of the graph in general, it'll have the same end behavior as long as a is negative. So as x approaches negative infinity, that's the graph going to the left. So the left side of my graph finishes upward. So that means that f of x approaches positive infinity. And then as x approaches infinity, that's the right side of my graph. The right side of my graph goes down. So f of x approaches negative infinity. And then notice here, same thing, it's finishing, going in different directions. One side is up, one side is down. So your end behavior should go in different directions as well. One thing to keep in mind before we move forward is no matter how complex the function itself is, if you can identify like what the lead coefficient is, you can determine the end behavior. That's really all you need to know. If it's the lead coefficient is positive, you're going up and to the right. If the lead coefficient is negative, you're going down and to the right. Think like positive slope and negative slope. And that's whenever there's an odd, like, powered function in general. Okay, so next section, if a cubic function has a relative max or relative min, it can occur between zeros or at a zero of the function. So there's kind of two different options. It can, I'm getting ahead of myself. I'm just going to read the next section. You've heard me say like a little bit, a few minutes ago maybe, the multiplicity. So the multiplicity of a root is the number of times that the linear factor appears in factor form of the polynomial. So I don't know why that got cut off, but for example, in this function, f of x equals x plus 3 squared times x minus 2, the factor x plus 3 is squared. So that means that its multiplicity of like the 0 that comes from it. So like if I were to set this x plus 3 equal to 0 and solve it, it would give me x equals negative 3. So the 0 that comes from it is x equals negative 3, and its multiplicity is 2 because that factor is squared. Okay, these next two bullet points are really important. So if the multiplicity is odd, then the graph crosses through the x-axis at the 0. So like, for example, this exponent right here, there's none. So it'd be like a first power, so that's odd. If it's to the third power, to the fifth power, any odd number, that means that it crosses through the x-axis at the 0 that goes with that factor. If the multiplicity is even, that means that the graph bounces off the x-axis at the 0. So for example, this is even because it's the second power, so it would bounce off of it. I'm going to draw like a really quick sketch. This is not something that like you're expected to know how to do yet, but I just want to show you what like the crossing through versus bouncing off is referring to. So the 0 that comes from this factor we just talked about is x equals -3, because you would do like x plus 3 equals 0 and then subtract the 3 over. From this factor, it's x equals 2, because you do x minus 2 equals 0 and then add the 2 over. And then this multiplicity for the x equals -3 is 2, which is even. And then this multiplicity is 1, so it's odd. So that means that this x equals -3 is going to bounce. And then this one is going to cross for the x equals 2. That doesn't have to mean anything to you yet. Like, this is the first time you're seeing it. You'll learn how to do this on your own as well. So if I have a graph that I just want to sketch, I have a 0 at -3. I have a 0 at +2. I'm not going to get too far into end behavior, but basically like when you draw your graph, it's going to bounce off -3. At some point it will turn around and it'll cross through at +2. This is what multiplicity tells us, is that it's supposed to bounce off here and cross through here because of the powers that are happening around those factors. Okay, so next example, example 2. Find the following key features of f of x equals -x cubed plus 3x squared plus x minus 3. This is the same function we already looked at in the first part of these notes. So we already kind of have some of this information that we'll need. We're just going to go piece by piece. So for end behavior, we just have to determine if a is positive or negative. This is in standard form. The lead coefficient is -1. So it's negative. So it's going down and to the right, like a negative slope would be. So as x approaches -infinity, that's the left side of my graph. The left side of my graph goes upward, so f of x approaches positive infinity. As x approaches infinity, that's the right side of my graph. The right side of my graph goes downward, so that would mean that f of x approaches -infinity. If drawing this little like sketch that I just did on like the upper right here doesn't really click, it's okay. Like, this problem really can be like kind of copy and pasted, for lack of a better term. So like if you're just like really struggling to like fully grasp end behavior, as long as you can recognize, okay, the lead coefficient is negative, so I could just go back up to the notes right here and it would be the same end behavior as the negative lead coefficient up here, assuming we're just talking about cubic functions in general. So same exact answer. Okay, so the next part, I'm going to go to the right here. So for positive and negative intervals where the function is above or below the x-axis. Remember, positive or negative is just like, you know, if I have a little sketch, it would be positive right here and right here because it's above the x-axis there. Negative down there and down there because it's below the x-axis is what positive and negative means. So in order to do that, we'll find the zeros. We already did that, so we're just going to copy that work down. And then we'll use the end behavior to sketch the graph. So this was example 2 from the first part of the notes. Yeah, the same exact function up here. So f of x equals -x cubed plus 3x squared plus x minus 3. We already found the zeros there. It was these. So we're not going to do all that like factoring work again. We're just going to take that same information. So x equals 3 and then -1 and +1. So the zeros are x equals 3, x equals -1, and x equals +1. That's honestly enough to sketch the graph, and like big emphasis on sketch here. So I'm going to draw an x and y axis, and then I'm not going to scale the y axis really, because again, it's just like a sketch. I'm going to make this a little bit bigger actually. I'm not going to scale the y axis at all. I am going to scale the x axis so I know where to put my zeros on there. So I'll go up to 1, 2, 3 on the positive x-axis, and then I just need to go down to 1 on the negative side, because that's my like smallest x value. And then I'm going to put points there. So at x equals 3, at x equals 1, and at x equals -1. And then from there, I can use my end behavior to finish my sketch. So the end behavior, I'm going to redraw that little like sketch that we used for the negative end behavior. So think negative slope, it goes like this. So that means that the left side of my graph finishes going upward. So from my leftmost point, which is this -1, I'm just going to draw a line going upward. And then if my like end behavior has a negative lead coefficient, that means that it's going down and to the right. So for my rightmost point, which is the 3, I'm going to draw a line going downward. And then we have to think about like the multiplicity of these like roots and stuff, and we can go back to when we factor to find it. If I go back up here really quick, I know this is a lot, I'm sorry. If I go back up here really quick, this is the factored form. No, it's not. This is the final factored form. And none of those factors, so there's the like x minus 3, x or 1 plus x, and 1 minus x, none of those factors is being squared or anything like that. So all of their multiplicity is just 1. What that means is that you're not going to bounce off any of the zeros, you're just going to cross through. So I would cross through at -1. We would turn back around at some point and cross through at 1, and then cross through 1, turn back around at some point, and cross through at 3. And like these, where we're turning around, big estimate sketch. Like we don't know those, and that is okay. Okay, so now that sketch though, even though we don't know like these exact points, is enough to tell us like where the function is positive and negative. So we're positive right here and right here. So that this is to the left of -1 would be -infinity to -1. So we're positive from -infinity to -1. And then that second little green section, that's between 1 and 3 when it's like above the x-axis. Remember that you're always looking at just like the x coordinates where it's crossing the x-axis to see like where it's going from positive to negative. So this would be between 1 and 3. So another positive interval between 1 and 3. And then for the like negative parts, it's negative down here. So that's between like the x-intercept -1 and +1. So it'd be from -1 to +1, and your interval should always have the smaller number on the left and the bigger number on the right. And then for the last one, it's negative on like that side, the right side of the x equals 3. So it's like negative starting at 3, and then if it's on the right side, it'd be going to infinity, so 3 to infinity. Okay, so those are our intervals for whether positive or negative. And then for the relative max and minimum, again, these are just estimates. Like we don't know exactly. You would have to use like a graphing calculator to find them. So use the sketch to find sample points. we're just trying to figure out like an area where it's changing direction and then use those points as input values to find like the height of them. So what that means is like, maybe around like right here, it's changing direction, or like right here is changing direction. So we can just, actually, I'm going to say right here, just since I don't want to put in a decimal, I don't want to make it life harder than it needs to be. So we can say right there it's changing direction, and then right here as well. Technically, we know this point, but I'm going to pretend like we don't. It's the y-intercept. We already found that. But I'm going to pretend like we don't just for the sake of finishing our estimates. So I found those two values. I'm going to say this is like 0, comma something. Again, we know what that is. It's the like -3, but just for the sake of seeing like the example, I'm going to leave it as if we don't know it. And then this point right here it's between 1 and 3, so that would be an x-coordinate of 2. And we don't know the heights of those points. We don't know if those are the exact max or min. We're just guessing that they are where they change direction. If we're wrong, it's okay. We're just estimating. So then now to find like what y values go with them, we have to put those as our like input values into our function. So we'll do f of 0 first, and that just means that I take that 0, like x coordinate, and I put it into the function where x is. So that would be -0 cubed, and then plus 3 times 0 squared, plus 0 minus 3. And then we've already done that work. All these simplify and cancel out, so we're just left with -3. So this point is 0, -3. And then that one would be, I'm going to actually leave that to the end. So we have this point where it changes direction at 0, -3, and then we'll talk about the max or min at the very end of this. And then the second point that we wanted to check where it changes direction is up here, and that has an x value of 2, so we would do the same thing, but we would plug in x equals 2 instead. So we'd find f of 2 equals -2 to the third power, and then plus 3 times 2 squared, and then plus 2 minus 3. We just put the 2 into all of these x's instead, and then now we'll simplify. So this is just, the negative is not being raised to the third power. Again, it would have the same outcome, but just for the sake of not messing that up later on down the road, leave the negative out in front. And then 2 to the third power is 2 times 2 times 2, so that's 8. And then this is 2 squared, so 4 times 3 is 12, plus 2 minus 3, and then from there we can combine all those. So -8 plus 12 is 4, and then plus 2 is, why can't I add 4 and 2 is 6, and then minus 3 is 3. So we end up with 3 right here. So that's the point 2, 3. So this height is 3. And then we just want to decide if those are like maxes or mins. I'm going to rewrite those points over here where I have a little bit more space. So 0, -3, and then 2, 3. So now we just have to decide whether they're max or min. So for 0, -3, that is this point right here, and it's directly below the point surrounding it. So that would be a relative minimum. So 0, 3 is a relative min. And then for 2, 3 up here, it's directly above the point surrounding it. And this isn't just like your sketch should look the same. Like it doesn't have to look exactly the same, but it'll have like a point in that general vicinity that is also higher than the point surrounding it. So it'll always have a relative, in this case max, around that area. So like I said, 2, 3 is around the points, or is above the points around it, so it would be a relative max. Okay, so these problems, I had a feeling they were gonna take a really long time. So I'm gonna save example 3 and put it in like a different video just for the sake. You can watch it as an extra example if you would like to, but I'm gonna include it in this one. I'm gonna go down to 13.3. Okay, so graphing cubics from rules, we're just going to use all of the key features and stuff like that. So example 1 is f of x, and this is the last example. So example 1 is sketch a graph of the following function using its key features. It's f of x equals x minus 4 times x plus 2 times x plus 5. We use this as our very first example in 13.1. Not going to redo that work, just going to take the stuff from up above. So domain, I'm not going to scroll, but domain of any cubic is all real numbers, so that's negative infinity to positive infinity. Range, same thing, negative to positive infinity. For the y-intercept, remember that's like when you put in f of 0 and you put zeros in for all of the x's and simplify. Like I said, we did that work up here. That was like the very, very, very first problem we did. So this whole section was where we found the y-intercept for the same exact function. So our y-intercept was at 0, negative 40. So just to save a little bit of time. Okay, so y-intercept is at 0, negative 40. The x-intercepts are a little bit easier to see without scrolling. So for the x-intercepts, remember you put 0 in for f of x, and then you set each factor equal to 0. So x minus 4, x plus 2, x plus 5. And if I were to set each one equal to 0, I would get x equals 4, x equals negative 2 because you'd have to subtract the 2 over, and then x equals negative 5 because you'd have to subtract the 5 over. Again, work is at the top of the page or at the beginning of the notes, so if you need to go back to it, you can. And then those x-intercepts are at 4, 0, negative 2, 0, and negative 5, 0. And then for the end behavior, we're looking at what our lead coefficient would be. So I know it's not in standard form, so it's hard to see, but the lead coefficient would come from multiplying all of our x's together. So this is just like a 1x times 1x times 1x. So the lead coefficient would just be a 1x cubed because none of these x's have a lead coefficient, and that's what it's going to come from, is those three multiplied together. So our lead coefficient, I'm going to shorten it as LC, is positive. That means that it has not like a positive slope, but trends like a positive slope, so it goes up and to the right. So for our end behavior, as x approaches negative infinity, that's the left side of the graph, it's going downward. So f of x approaches negative infinity. And then as x approaches infinity, that's the right side of the graph, it's getting bigger. The graph is going upward, so f of x approaches positive infinity. And then the relative max and min we can't find until we really sketch it. So their graph. And then I'll put my zeros on the graph. I'm not going to worry about scaling the y-axis yet. I'm just going to put my x-intercepts on there. So I have to go down to negative 5 and then up to positive 4. And then I'm going to put my x-intercepts on the graph right away. So 4, 0, and then negative 2, 0, and negative 5, 0. And then we know our y-intercept is at negative 40. I'm not going to do like a million, 1, 2, 3, 4, all the way down to negative 40 because I don't know any other points on the y-axis, so I don't need to scale it that way for a sketch. I'm just going to do one line and label it negative 40 and put my y-intercept right there, and that's totally okay. These are ones on the x-axis though. Okay, and then if we look at what the multiplicity is of all of our roots, none of these factors are being raised to a power. They're just all the first powers. They're all odd, meaning that they cross through, not bounce off. This example that I skipped that I'm going to put in a different video is going to have an example of something where the graph should bounce off. So if you have questions about that, definitely watch that later, but maybe take a break after this video. Okay, so our end behavior. We just based on our little sketch, it's going down and to the left. So from my leftmost point, I'm going to go downward. And then it's going up and to the right. So from my rightmost point, I'm going to go upward. So my end behavior is taken care of now. And then for all of my zeros, they all have a multiplicity of 1. So I'm going to cross through each one of them. So I'm going to cross through at, this was -5, and this was 4. I'm going to cross through at -5. I will turn back around somewhere, don't know where, just an estimate, and then cross through at -2. And then I have to turn and go through my y-intercept. It's not like guaranteed that the y-intercept is a relative min or a relative max. We're not really sure, but it is going to cross through there at some point. I'm going to keep going like down past it before turning around. But again, like we don't know. So if you turn around at the like y-intercept, it's okay. Like it's not incorrect. We're just doing our best to sketch it. And then that links up with my like last 0 of having to cross through it and match up with my end behavior. If you ever like bounce off wrong or have your end behavior wrong, something won't like line up. So it's kind of like a way of checking your work and stuff. And then to find the relative min or max, we have to estimate those points. So I'm going to say there's one right here. That would be at -3 something. And then I'm going to say there's one right here, and that would be at 1 something. And then I only know like the x values of those points where they're changing because they're like between my zeros and stuff, and that's why we're able to pick like -3 because that's between -1 and -5, or 1 because that's between, well, technically like -2 and 4. I think I said -1 and 5, but I should have said -2 and 5, sorry. Okay, so we know the x coordinates, we just have to put them into the function to find the y coordinates. If it's not the exact max, that's okay because it's just an estimate. So this one up here, the -3 comma something, is going to be my relative max because it's like higher than the point surrounding it. So to find the relative max, I would take that -3 and plug it into my function where x is. So it's going to go here, here, and here, and then I'm going to simplify. So I would find f of -3, and then it would be -3 minus 4, and then times -3 plus 2, and then times -3 plus 5. Simplify each parentheses first, and then multiply them all together. So -3 minus 4 is -7, -3 plus 2 is -1, -3 plus 5 is 2. So it's 7 times -7 times -1 is +7, and then times 2 would be 14. So the y coordinate for this point would be 14. Whatever you get out is the y coordinate, and that y coordinate is the max because it's the height of that point. You don't need to like label the y-axis or anything like that. You could just state what the max is. It's 14. Estimated max. Relative max. Sorry, estimated relative max. There we go. Okay, and then the last little part, this point right here at like 1 comma something that we were estimating as a like change of direction is a minimum because it's lower than the point surrounding it. And then to find the actual height of the point, I'll take that x equals 1 and put it in for all of the x's in the original function. So I would find f of 1, and then it would be 1 minus 4 times 1 plus 2, and then times 1 plus 5. So we'll take those, multiply them all together. 1 minus 4 is -3, and then 1 plus 2 is 3, 1 plus 5 is 6. So it's -3 times 3 is -9 times 6 is -54. So that height, that -54, the output value is the height or the y coordinate of our point. So we did good in like not making the -40 like the y-intercept or change of direction because we ended up getting lower from there. So this isn't guaranteeing that like this is the correct point, but it was a good estimate to say that it didn't change direction at the -40. So then that height of that point, -54, the y coordinate, is our relative minimum.